Hey guys, I'm Bad with Math, and today I'm going to be walking you through an AP Precalculus Practice FRQ. So in this video, we're going to be following the 2024 exam FRQ number 4. And in part A, we're given the functions g and h, where g of x is equal to e to the x plus 3, and h of x is equal to arcsine of x over 2. And both of these parts in part A are asking us to solve for when our function reaches a specific value. So we're going to look at the first part over here where g of x is equal to 10. And we're trying to solve for x in the domain of g. And what's important is that we have to consider the domain of g before we begin. Now, since the domain of g is all real numbers, it's not going to be an issue for us when we solve for x. But we're going to see in the second part how we would maneuver that. So here we're just going to make g of x equal to 10. Our g of x is e to the x plus 3, and this is going to be equal to 10. From here, we have to think of how to isolate x. And given that the power x plus 3 is being raised to a power of x plus 3, we can use the natural logarithm, which is the inverse of the number e, in order to bring down that x plus 3. So if we make both parts of the equation the argument for the natural logarithm, we'll be able to cancel out ln and e, and we'll be left with x plus 3 equals ln of 10. And then from here we can just subtract by 3, which will give us an answer of x equals ln of 10 minus 3. And that's 1 point on the FRQ already. Now here we have to do a similar thing. We have to solve for h of x equals power of 4 for values of x in the domain of h. And what we notice is that whatever we plug into our argument of arcsine, or also known as inverse sine, right? So I'll just write as inverse sine as well. Whatever we plug into the inside of the parentheses, the argument, so x over 2, has to come out as some value in between -1 and 1. So x over 2 has to be some value in between here. That's just something to keep in mind for when we find our answer. So now let's plug in h of x, which is going to be, I'm going to use sine inverse, but it's the same thing as arcsine. Sine inverse of x over 2, and this is going to be equal to power of 4. So in order to cancel sine inverse, we use the inverse of sine inverse, which would be sine. So I'm just going to apply sine to both sides. That should cancel out this part. So we'll be left with x over 2 equals sine of pi over 4. And we know from our unit circle that pi over 4 is going to be the square root of 2 over 2. And if we take a look here, the square root of 2 is some number greater than 1, but it's going to be less than 2 because the square root of 4 would be 2. Which means that we have some number between 1 and 2 divided by 2. So this number is less than 1. And when we look back at our domain, x over 2 has to be in between -1 and 1, which we see if it's less than 1, it is going to be in this domain. So we can just work with this number. But that's something that we have to look out for in case we got some value that was not in our domain. But we can carry along, and then we can just multiply by 2 to cancel out the 2's, and we'll be left with x equals the square root of 2. Okay, so now in part B, we're given two new functions, j and k, where j is this long logarithmic expression, and k is this long trigonometric expression. So in our first part, we're asked to rewrite j of x as a single logarithm with a base of 10, which makes sense because all the logarithms here have base 10. The first thing I'm going to do is I'm going to just write down, I'm going to look at my logarithm for a moment, and I notice that we have everything in the logarithm here. Like, if we compare these two and this one, we notice that there's a 9 on the outside being multiplied with the logarithm. So what I'm going to do is I'm going to change that using my logarithm rules. So I know that if I'm multiplying a number or anything by a logarithm, I can move the 9 basically to be the power of the argument of the logarithm. So what I'm saying is that I can basically move this 9 to be log base 10 of x to the 9th power. And then from here, we know that if we're adding two logarithms to the same base, we can multiply their insides together. And if we're subtracting, we can divide. So what I can rewrite this as is one giant logarithm, which I'm going to do this. And we know that 8x to the 5th is being multiplied with 2x squared because the logarithms are being added. But then we also know we're going to be dividing by x to the 9th. So I'm going to divide this all by x to the 9th. Then I'm going to simplify the top really quick. We'll get 16 x to the 7th over x to the 9th, which means that our final answer for j of x is going to be the logarithm base 10 of 16, and if we see x to the 7th over x to the 9th, we'll have x squared on the bottom. Now with k of x, rewriting it as a single term, we have to involve tangent of x in our single term. And so the difficult part is that we're going to have to know our identities. So what I'm going to write beforehand, because I know what we're going to be using here, is I'm going to write my Pythagorean identity. So cosine squared of theta plus sine squared of theta equals 1. And I'm going to also write what tangent equals and what secant equals. So tangent of theta is cosine of, no, it's sine of theta. Sine of theta over cosine of theta. And secant of theta is just going to be 1 over cosine of theta. So that I can reference these identities back when I am rewriting k of x. So my first step is I'm going to use my Pythagorean identity. I'm going to think for a moment. So I have cosine squared plus sine squared equals 1. And if I were to minus sine from both sides, I know that cosine squared equals 1 minus sine squared, which basically means if I have 1 minus sine squared here, and that's equal to cosine squared, I can input cosine squared to the top of the numerator there. So I'll have cosine squared of x over sine of x. And then I'm going to replace my secant of x with 1 over cosine of x. So let me erase this part here. 1 over cosine of x. And then from here we can just cancel out this cosine of x and one of these. So we'll be left with k of x equals cosine of x over sine of x, which we know that tangent is sine over cosine. So this is really the reciprocal of tangent, meaning if it's a reciprocal of tangent, we can just say it's cotangent of x, but we want to rewrite it as a single term involving tangent of x. So instead of writing cotangent of x, I can also rewrite it as 1 over tangent of x. For this last problem, we're given just one part, and we have our function m, which is the inverse cosine of tangent of 2x. So it's a double composition. And then we're trying to find all values in the domain of m that yield an output value of 0. In other words, this just means when m of x is equal to 0. So that's exactly what I'm going to do. I'm going to set m of x equal to 0. So m of x is equal to cosine inverse of tangent of 2x, and this is going to be equal to 0. And we're just going to apply cosine, right, to cancel out the cosine inverse there. and we'll be left with tangent of 2x, which is going to equal to cosine of 0, and cosine of 0 is 1. And then from here, to isolate 2x, we're going to apply the inverse tangent, right? Inverse tangent. And then basically, when is tangent equal, sorry, I meant to, little brain fart there, I meant to put it over here. What this is saying is when is tangent equal to 1? And we know that tangent is equal to 1. Tangent is in case you only have your sine and cosine memorized, tangent is sine over cosine. And so what we're looking for is on the unit circle, when is tangent equal to 1? When sine and cosine would have the same value, right? If they have the same value, when you divide a number by itself, you get 1. And we know that the angle pi over 4, that our values are going to be root 2 over 2 and root 2 over 2, which means at pi over 4, tangent is equal to 1. Additionally, at 5 pi over 4, on the standard unit circle, we have both of these values just negative. So we'll also get 1 as well at these two values, at pi over 4 and at 5 pi over 4. And if you continue adding pi to pi over 4, you'll end up, you'll continue having angles that if you plug them into tangent, you'll get 1. So what I mean by that is, like, if you're given tangent of 9 pi over 4, for instance, you would be getting the same value as if you plugged in pi over 4. So how you would write that here is, we know it's at pi over 4, and then we know that every time we add pi, we're also going to get that same value for tangent. And this can go an infinite number of times as long as you're adding pi. So I'm going to write an n here, and I'm going to specify that this n is for any integer. So it could be like 1 pi, 2 pi, 3 pi, negative 3 pi. It doesn't matter, but that's essentially what it means. You don't have to write this statement down on your actual FRQ, but you do have to include the n. So from here we can just divide by 2. And now we'll be left with x equals pi over 8 plus pi over 2 times n. And this would be our answer. If you had only included like pi over 4 or 5 pi over 4, for instance, if you had only included one value for x, you'd only get 1 point on this FRQ. Including this second part, the plus the coefficient and n, you get that second point because it's asking for the domain of M, which means that any angle measure that you plug into the argument of tangent, that would give you 1. So yeah, that's how you would do FRQ number 4 on the AP Precalculus exam.